Good morning. It's Prabchintan Randhawa from Austin, Texas. It's Saturday, January 10th, 8:24 a.m. Happy New Year. Woke up, gotta make breakfast, drink coffee, clear some emails. I need to do tax stuff. I feel like I'm always doing tax stuff, but I figured I will do the same combination I've been doing the past few weeks. I really enjoy it, making food, doing stuff, clearing out my email, listening to this stuff. Streaming gives me good practice to do live things. I noticed last couple of times there was a skip thing happening. Like on my end, it plays fine, but on YouTube, it tends to like skip and glitch. But let's see if that happens. I've tried to change a few settings on my end. Other than that, yeah, Happy New Year. Everything's good. I feel like I had a good last year. Maybe I should do longer monologues and talk about what is happening in my life, but we'll see if that happens. Enjoy. Nothing more to say today.
Hello, everyone. Welcome to our first Q&A about history of science and technology for 2026. I see a bunch of questions saved up here. I see one from Gary. How would you rank 2025 in the history of science and technology? Would you say the last decade has been important or just a small mention in the grand scheme of things? That's harder to answer than one might think. This year, drama, not so much that immediately comes to mind. Last decade, I'd like to think some of the things that I've been doing are actually fairly significant in the overall arc of the history of science. I think that the other big thing was the ChatGPT surprise and kind of the arrival of kind of the sort of the next step in AI that works type thing. I think that the implications of that for both, well, it's sort of interesting to go back and look at computation in general, because the first big effect of computation in general, starting when computers were introduced in the 1950s and got progressively more widely used into the 1980s with personal computers and so on, and then essentially ubiquitous computing in the 1990s and beyond. The first sort of effect on, for example, science from that was just you can use computers to do things. I think the second effect that I guess I was much involved in starting in the 1980s is the concept of computation, using the idea of defining rules and seeing what they do, using that concept as a way to think about sort of the foundations of science itself. And that's a thing that has been sort of gaining in importance over the past few decades. And it's something where not only computers as practical things, but also computers as conceptual things. That's been a very important thing, and there's more to run on that in many ways. I think it's the same story with AI and LLMs and so on. There's oh, you can use an LLM to, summarize this document or something like this, that's one sort of implication of LLMs and so on. The other implication is a conceptual one. If you say, well, what's really going on in brains? Can we tell if there has to be some new physics that makes thinking work in the brain? Well, we can kind of see that that probably isn't the case, because we know we can reproduce an awful lot just by using things like LLMs. So I think there's a lot of kind of conceptual mileage that is probably still to come from the success of LLMs in kind of replicating some aspects of kind of human thinking. Humans still do different things and will always, because the only thing that's going to do exactly the same as a human does is a human, not, a box on your desk or a thing in a cloud, in the cloud or whatever else. But I think the question of there's sort of more conceptual mileage to come from sort of the surprise of the fact that, yes, you can get artificial neural nets to do all these things that we thought were human-only type activities. I would say in the overall arc of what's happening in science, if we look at kind of the last century, let's say, I would say the beginning. Well, let's go back several centuries. Let's talk about the bigger arc of the history of science. First question is, well, what is science? I see science as being mostly about taking what happens in the world and finding a way to make a human narrative that explains or lets one understand what happens in the world. You see some planet going around the sun or whatever. You just say, well, it does what it does. Or you can say, I've got a story about why it does what it does. There's this force of gravity and it's an inverse square law, and I can solve these equations and all those kinds of things. Science is about finding these ways to take what exists in the natural world and describe it in human terms. Another aspect of science, which sort of somewhat connects to technology, is, well, what do we actually notice in the natural world? Without telescopes, we didn't notice a lot in astronomy. Without microscopes, we didn't notice a lot in biology. Without other kinds of sort of tools for noticing things, where we don't, there's less grist, there's less that we want to talk about scientifically, so to speak. But the actual content of science ends up being typically this, is there a narrative that we can give from what we can see? Now, even the what we can see question has advanced in interesting ways over the years. I mean, basically, it's, well, let's talk about the sort of the general arc of these things. I mean, so first thing is, in antiquity was the time when people started making lists of things. People started trying to systematize things. Aristotle was making his lists of sea creatures and forms of argument. And other people were making, in Babylonian times, people were making lists of types of words or gods for this or that, or stars or things like this. People were sort of trying to systematize things by making lists of things. People were also trying to introduce things like units of measure. How many of these things do we have? How much of this do we have? First there's numbers, you can count sheep or whatever. Then there's how much gold do we have here? Well, it depends on how much it weighs. We have to have a uniform unit of measure. So those are things which sort of start to systematize kind of describing the world. I think at some point in the middle of that, the notion, which already existed in things like Aristotle and others, of species of critter. Oh, there's this kind of bird and that kind of bird, rather than just like we can sort of distinguish things in the world by those different categories. Well, so what became of science at that time? A lot of science at that time was really mostly talking about sort of the structure of things. What are things made of? Those kinds of questions. It wasn't a lot of, there wasn't a lot where you could say, kind of this is a small scientific theory. This is a small to describe theory. And then there's all this stuff you can deduce by going many, many steps in the theory. It was mostly pretty at the surface. It's like, this thing does this, and that's what you know about what it does. Now, so that was the thing that existed basically until the 1600s. In the 1600s, well, several things happened. I would say that kind of one thing was mathematics had developed further. So, I mean, the history of that was in the Babylonians were the people we know who introduced a lot of kind of mathematical ideas. Then in Greek times, kind of the notion of proofs and things like this came in. I would say that the question of it was really much more you can work out things with numbers. Numbers were a thing that were understood. You could work out things with numbers. Then from people like Euclid and so on, we can have geometrical figures, and we can do things where we can deduce things about geometrical figures. The big advance that happened in the 1400s to 1500s was the introduction of algebra, the idea of being able to talk more abstractly about things like numbers, not just say the particular number 75, but the thing that we call x that can represent any number. Now, many of the same kinds of underlying concepts had already existed in antiquity. People like Archimedes and Diophantus and so on had things that were tantamount to sort of filling in variables, but they didn't think of them that way. They didn't have a notation for describing, for setting up algebra and so on. I think it didn't help that in those days, letters were used to represent numbers, whether it's the Roman numeral system or whether it's the Greek numeral system where you're actually using alpha for 1, beta for 2, things like this. And that meant that introducing another thing that was kind of a letter that stands for a number, but numbers are already represented in terms of letters. It's very confusing. I think it took the introduction of Hindu-Arabic numerals, which happened in the West around 1200, to sort of have a thing where you could very obviously distinguish numbers as you wrote them down explicitly from a thing that stands for a number but isn't itself a number. Now, confusingly enough, some of that concept had already come in even with Euclid. Euclid had figures where there was represented a geometrical figure, and you would label an angle, and the angle could be labeled with a Greek letter, and they were labeling angles with letters, even though those letters also stood for actual numbers, which weren't the numbers that were the actual angles of those in those geometrical figures. In any case, the end result of all this is 1400s to beginning of the 1500s, kind of the introduction of algebra and the development of mathematics, where you could actually work out a lot more with the math than you had been able to before. You would go many more steps in doing the math. Well, then in the 1600s, sort of one of the big ideas was the kind of merger of that kind of more sophisticated math with the things that you could actually study in the physical world. So, for example, Galileo introduced some kind of mathematical ideas, like, you drop an object and it falls, and it's the distance it goes up quadratically with the time that it's taken, and so on. And so that idea that you could kind of have a mathematical formula that represents something in the physical world, that was a kind of a thing that was coming in the beginning of the 1600s with Galileo. Then sort of the big advance in the late 1600s with Newton and so on was the introduction of calculus, and the idea that you could be much more sophisticated in introducing math into kind of the description of the natural world. And that worked well for the motion of planets and things like this. It worked well for mechanics. It didn't work at all well for things like biology, didn't work well for some more complex physical processes and so on. Now, interestingly enough, in the 1600s, two other advances happened that also moved science forward. One of them was the telescope, the other was the microscope. So telescope around 1608 was let one kind of explore the richness of the astronomical world, or begin to at least, in a way that hadn't been possible before. And then the microscope let one start looking at biology and looking at, I think the most important things that people put under microscopes were things like biological cells. And that was Van Leeuwenhoek and Robert Hooke and so on, starting to examine what these very complicated things that are you know, the construction of biological organisms, of life, what to tell something about what's going on there. So sort of in the 1600s, these three advances of mathematics as a formalization of science, and then the what's out there from telescopes and microscopes. I would say that the telescope side of things, the mathematicization, the formalization of celestial mechanics, was vastly more successful than any kind of formalization of things you could see. Actually, also in the 1600s, work on crystallography, one place where you really can kind of apply math easily to microscopic things. You have crystals which have definite geometrical structure and so on. And that was another thing that I think from about that time. So, you know, if we then look at, so big sort of explosion of things that became possible in the 1600s in science. The 1700s, a lot more kind of development of the mathematical side of things, a lot more understanding things like partial differential equations coming in, representing fluids and solid mechanics, things like this. And then I would say in the 1800s, kind of a couple of things going on. One thing was the attempt to quantify more kinds of things in the world. The attempt to sort of put numbers on things, including things in biology, including things in sociology, not very successfully, including things in economics and so on, that there were kind of the quantification of more kinds of things was something that was definitely happening in the 1600s, and by that point, kind of a certain level of mathematical sophistication, enough to do sort of most of classical physics, had, or what could be done with traditional mathematics and classical physics, so the raw material existed in the 1800s to do that. But I would say that the next kind of really big breakthrough period was the late 1800s, and the introduction of kind of a higher level of formalization of things, a higher level of abstraction of things. I mean, in biology, there had been 1859, you know, Darwin's Origin of Species. That was kind of a zoom out and look at the big picture of biology in a more abstract way. And the notion that, oh, there are all these different species, but, you know, maybe there's something in common that we can say about all these species, and hence natural selection and so on. Late 1800s, it's really a thing that in both physics and particularly in mathematics, this notion of let's formalize things. Let's try to have something, for example, in mathematics, let's try to understand, we've got the particulars of mathematics, you know, geometry, algebra, things like this, just as we have the particulars of mammals and birds, but what's the zoomed out version of what mathematics is like? And that led to things like Hilbert's program and this kind of notion of saying, let's just have sort of formal rules that describe what's going on underneath mathematics and use that as the kind of thing that we situate mathematics on. Somewhat the same kind of thing with physics, but then sort of the big successes of physics at the beginning of the 1900s, some of them were the result of experimental advances. Some of them were kind of conceptual kinds of advances. I think that the three big things that came in well, eventually in the 20th century, statistical mechanics, relativity, and quantum mechanics. Statistical mechanics had been sort of initiated in the mid-1800s, and it was kind of the idea of don't just try and describe everything that's going on. Just say in the aggregate, sort of zoomed out, what happens with all those gas molecules. Don't try and trace each gas molecule. Just say, what can you say about all the gas molecules together? And that led to things like the second law of thermodynamics and so on. And that was kind of an idea different from the ideas that had been had in kind of the Galileo-Newton tradition of mathematical science, of just, let's figure out exactly what's going to happen to everything. This was, let's look at a whole bunch of things and statistically say what happens in the aggregate. And I think then, I would say, in both relativity and quantum mechanics were, in a sense, the greater formalization of physics. Whether it's in relativity, being able to just sort of talk about coordinates in a more abstract way, whether in quantum mechanics, it's kind of talking about the states of things in a more abstract way. Both of those advances actually had another piece to them, which was the question of, well, just what are you trying to compute in physics? Are you trying to compute something that is absolutely there, or are you trying to compute something that is relevant for what we observe to be there? And both relativity and quantum mechanics began to bring in this idea of the observer as being something that you had to sort of account for in the science of things. Well, the other big advance around that time was in chemistry, and sort of the systematization of chemistry in the 1800s, whether it's the periodic table, whether it's the notion of chemical reactions, being able to identify definite elements and know what was sort of involved in chemical compounds, what was happening in chemical reactions. That was kind of a thing in the 1800s, where at first it was kind of almost a kind of a numerological kind of thing. Oh, we need this amount of hydrogen versus that amount of oxygen and so on. But then increasingly that sort of got formalized, and eventually it got physicalized, so to speak, of actually understanding what were these molecules and chemical elements and all that kind of thing. But chemistry got a long way without really understanding the physicalization of that and exactly what the structures of molecules were and so on. And so just a huge amount of data accumulated in chemistry. And by the late 1800s, the chemical industry and lots of kinds of the work, the development of kind of, actually being able to make chemicals and compounds that were not naturally occurring, or make them in much larger numbers than they occurred in nature. That was the thing of the late 1800s, early 1900s. That was sort of a huge direction in science, was to catalog all that stuff. I mean, by the way, in the 1700s and 1800s, another kind of big form of cataloging that was going on was in biology, of natural history, and just like, what are all the critters of the earth? I suppose that had followed on from the kind of geographical efforts to kind of catalog, well, what is there on the earth, make maps of everything, and so on. So this kind of the natural history cataloging of critters, the chemistry and chemical industry kind of cataloging of different kinds of chemical compounds and so on, that was a thing from the 1800s and such like. Now, the next sort of big thing that happened, I suppose, was the merger of chemistry and biology, and the kind of realization that you could think about biology in chemical terms, even though the actual kinds of molecules that were involved might be different from the kinds of molecules that one had studied in chemical reactions and so on. But there have been sort of numerological kinds of things discovered, like Mendel's laws for genetics, that started to become more quantitative and started to become more kind of chemical by the 1930s even. But then by 1953, the realization of the structure of DNA was kind of the big moment when kind of one could start having more kind of theoretical underpinnings for biology, much more that one could say about the mechanisms of biology. And that kind of from that time on developed molecular biology, and that has led to, in molecular biology, there have been a long series of major advances as we understand more about this very complicated molecular computing thing that is life, and is what we're all running on, so to speak. And it's been interesting that in the field of biology, there have been, if anything, sort of a series of kind of, oh, we now understand, these different aspects of organelles. We now understand these different kinds of signaling pathways. We now understand this different kind of molecular mechanism and so on. We now understand, how the immune system works, things like this, or begin to at least. And there's been a lot to discover there. It's a kind of a long series of, you look at more stuff and there's just more and more and more things. There's an infinite, it's kind of a place where in the history of biological evolution, just a lot of detail has been accumulated, and in progress in biology has been sort of uncovering more and more levels of that detail. I have to say that my own efforts in recent times to understand sort of the theoretical foundations of biology kind of tell one that what biology has given us is it's harnessed certain irreducible lumps of computation, stuck them together, and made things that let us operate in the world as we do. And if we start to get very, very obsessed with, well, why does it work this way rather than that way, there's really no answer to that. It's because the particular history of biological evolution picked up this lump of irreducible computation and not another one. And so one can fill textbooks talking about kind of the details of biology, and obviously they're very important to us for biomedicine and so on, but they won't have the same kind of arc of principled character that one might expect in other areas. I mean, in a sense, the biology textbook is a little bit like a history textbook. It's telling one kind of what happened to happen, so to speak. And it's a little bit more than a history textbook because it's kind of what happened to happen and turned out to work, in the sense that it produced a fit organism that can be like us now, so to speak. But I think a lot of things happened in biology. Now in physics, concepts, statistical mechanics, relativity, quantum mechanics, those were set at the beginning of the 20th century. And the story of the 20th century has been a story of kind of using those frameworks and then just finding more stuff that fits into those frameworks. So big advances in the 1950s and 1960s, actually starting in the 1930s, in particle physics, kind of in a sense, ultimate reductionist approach of saying, what's everything made of? Well, kind of in the early decades of the 20th century, well, we'd learned, there are electrons, that's 1897, I think, and then it's kind of, okay, there are atomic nuclei, then there are protons, there are neutrons by the 1920s, by the 1930s, that was known, and then there started to be these other particles, the muon, the pion, and then this whole zoo of other particles. By the end of the 1950s, there were scores of particles known that have been produced in particle accelerators. And then it was realized, well, actually, there's another level of particles, there are quarks and so on. And that was realized, then it was realized that sort of there are certain features of particle interactions, gauge theories and so on, and sort of things started to fit more together there. And eventually we ended up with things like the standard model of particle physics that sort of emerged by basically by the end of the 1970s, pretty much all those pieces were in place. But then, for example, my own personal history, I worked on particle physics in the late 1970s when it was having a very strong period as the mathematical methods from quantum field theory became applicable to study all sorts of things with particles. But I have to say, it is somewhat shocking to me that even though there was quite a lot of advance in those times, the amount of advance in particle physics since then has been very incremental. I mean, a lot of details have been filled in, but the big picture things one knew at that time are still the big picture things in particle physics. At that time also, I was involved in this actually, there was sort of the effort to connect particle physics with what happened in the early universe and with cosmology. There's actually been more experimental development in cosmology, to some extent astrophysics, but particularly cosmology, over the last few decades, mostly as a result of better instrumentation. I wouldn't say the theories have really advanced much. It's more been, we got bigger telescopes, we've got better image processing and better data handling and so on, so we can learn more about sort of how how things work out there in the 100 billion galaxies that exist in our universe and so on. But I think kind of conceptually, not, the advances in physics are, the big advances happened at the beginning of the century. And in biology, again, sort of the big advances were in the last century had to do with sort of the development of molecular biology and the notion that there were kind of digital things going on and that there were kind of pathways and networks you could draw and all those kinds of things. That's something which kind of had emerged by the 1960s and continued to develop, lots and lots of detail being discovered. I would say that a field like chemistry, for example, again, this is a continuing story of science, is there are periods of rapid growth, usually the result of new methodologies, and then there are long periods of incremental growth. Chemistry, for example, is a field which for much of the 20th century, well, much of the latter half of the 20th century, was in kind of incremental growth. I mean, things like materials science, which particularly concern properties of solids, which chemistry hadn't been very big on. I mean, chemistry is like you put the things in a test tube, usually in liquid form, and you see what they do. Materials science much more concentrating, and materials science sort of emerging in the 1970s to 80s to 90s, much more concentrating on solids and properties of solids and so on. And that's a thing that sort of has continued to advance there. But I think these different fields, they get to a point, then they kind of plateau for a while. I mean, the same thing happens in computer science, for example. I mean, computer science, a funny kind of science, because it's not really the same kind of natural sciencey type science as a lot of these other kinds of things, but it kind of emerged kind of in the 1960s to 1970s, and there was a certain amount that could be said about kind of the general things you can say about algorithms and so on, the general kinds of data structures you can consider. There was a certain amount that was rapidly said, and then there's just a huge amount of engineering detail that becomes technology that gets built on that. But in any case, the question had to do with the last decade, and I would say that and I was talking about my own efforts. I think the thing that we've been able to do in the last, well, it's been, I don't know, the sort of starting in the 1980s for me, one thing was use programs as models of the natural world. This is an important idea. It's an idea that kind of silently has sort of taken over a lot of areas of science. It's an idea that, yes, the mathematical equations idea from the 1600s got a long way, but just saying write down rules and see what their consequences are, that's a thing from the 1980s, basically, and a lot associated with my efforts, and that's something which has become kind of a general way to make models of things. It's kind of a general way of talking about the natural world, is not in terms of this is the equation that this thing follows, but this is the rule this thing follows. And the thing that is sort of the thing one might have said, back in a lot of biology, even from a long time ago, is like, well, this increases, that decreases. It's kind of very structural statements about what goes on. The point of studying, of defining rules and then working out their consequences, their long consequences, that's a rather different kind of thing. That's something where the underlying description is this kind of very structural description, but then there's a sort of a big lever that is, and okay, you've got the rule now let's work out what happens from that rule. Much like in mathematics, one might start off from some equation or something like this, and then there's a lot to work out about what the implications of that equation are and how it gets solved in particular cases. But I think the main thing that we're seeing in recent times is kind of the arrival of kind of rules and computation as a foundation for models of things. And then the question is, well, what is the bigger science that you can build around kind of rules and what they do? Just like the bigger science you can build around equations and what they do is basically pure mathematics. So what is the science you can build around sort of rules and what they do? I've been referring to that in recent years as ruleology, the study of abstract rules and what they do. And there's kind of a sort of a big picture of kind of what you can say when you take a computational view of the world. There's both how you actually connect that computational view of the world to natural science, and there's the kind of underlying stuff of what do these rules in and of themselves, the pure mathematics, so to speak, what do they do? I mean, in the mathematical approach to science, there's kind of the pure mathematics, which is thinking about math for its own sake, and then there's the kind of applications of that, of actually setting up the equations of mathematical physics or whatever else. I think the thing that is, to me, rather exciting in recent times has been that we understand a lot more about kind of rules for their own sake and what they do, phenomena like computational irreducibility and so on. And we can now take that, just as we could take pure mathematics and feed its consequences into science, as happened from the beginning of from the 1400s and 1500s and the development of algebra to the sort of, and then later the development of calculus, but feeding that into the connections to natural science in the late 1600s, going into the 1700s, we're now able to do that with these ideas about computation. And I guess the other, and that I think unlocks kind of the next level of progress in a lot of these fields of science, in physics, in biology, in mathematics itself, kind of understanding kind of this lower level structure of this kind of ruleological structure that exists in all these fields and kind of lets one make further progress in those fields. And I think it's sort of been exciting. Last 5 years or so, we seem to have unlocked that sort of direction of progress. The other thing that's emerged in that period of time is the increasing importance of the observer in defining kind of what happens, what we actually see. There is this kind of this ocean of formalization, but the question is, in that ocean of formalization, where are the islands that we actually live on? And you can say some things about that ocean of formalization, but they don't relate that well to the things that we actually perceive as observers of the world. And I think the realization that that's a thing you have to kind of bring in is an important realization, and it's something that it's become in the last few years, the realization that you can kind of derive the laws of physics from observers like us and their relationship to the Roolead and computational irreducibility and so on. So I think to me, I mean, maybe it's just, it's a self-centered statement at some level because I've been in the middle of doing this, but I think it's really pretty exciting what we've been able to do with both the sort of using the computational paradigm in science and now with the specifics of thinking in terms of ruleology, in terms of observers and so on, to actually make progress in having a different conceptual framework for thinking about these areas of science. You know, when it comes to science versus technology and so on, the thing I would say that from a technological point of view, of course, the two big things I would say that are sort of the great things of the last half century or so are computers and precision manufacturing. I mean, I think that I suppose in another important direction for us is things like pharmaceuticals and so on, and sort of molecular scale manufacturing things that do things at a molecular scale, so to speak. I mean, it's kind of always when you see a piece of technology and you're looking at some piece of electronics, well, you usually can't see what's going on because it's inside a microprocessor these days, but some kinds of technology, you know, you look at a rocket engine, there's lots of complicated things obviously happening there. You look at something in a biology or chemistry lab, there's just, you know, a vial of transparent liquid, but all the technology is the details of the molecules that exist in that liquid. So, but I think the things that, you know, computers are sort of the core of so much technology. Precision manufacturing is a key thing as well, allowing us to make all kinds of devices and sensors and actuators and so on that make use of physics, basically. But we can actually successfully make use of that physics because we have the ability